Hello, chemistry, Mr. McKee here, and I want to talk to you about mole ratio and heat of reaction. This is the next stop on our tour of stoichiometry. So the first thing we need to discuss is the difference between endothermic and exothermic reactions. So exothermic reactions are those chemical reactions that release energy. My favorite example of this is a campfire. When you burn a couple chunks of wood, you are releasing the energy that was stored in the chemical bonds within the wood. Okay, and that's what keeps us warm and lights up the night for us. Okay, endothermic is the exact opposite. Just think endo sounds like in. So this is when energy is going into the chemical equation. So this is when energy is required to make a chemical reaction happen. An example of this would be photosynthesis. So plants absorb energy from the sun and use that energy to synthesize sugars. Okay? So energy is going into the plant. So how do you recognize these? Let's start with endothermic reactions. So anytime you have an endothermic reaction, a lot of times you're going to see off to the right of the chemical equation. And by the way, this particular equation is the combustion of paraffin, which is wax. So this is a combustion reaction, you'll notice there. And off to the right, this is how you're typically going to see it. You will see a negative number if it's an endothermic reaction. That means you've actually lowered the energy of the chemicals involved in the equation. Now, of course, you haven't lost that energy because it still exists somewhere, and in this case, it's released as heat. So as paraffin combusts and changes into carbon dioxide and water, this amount of energy, negative 1.62 times 10 to the fourth kilojoules, are going to be released. All right. And again, it's a negative number to indicate that it's an exothermic reaction, which is a little bit counterintuitive. You would think when heat is released that might be a positive number, but that's not how it works. The reason it's negative is because we're lowering the energy of those chemicals, even though we're releasing energy. The other way you might see this written, and maybe this is more clear to some folks, is you'll have the energy written as one of the reactants. Okay, and in this case, it's going to be a positive number because it's on the product side. I said reactants, but it's actually one of the products, okay? So that's the other way that you're going to see it. If it's written as a product and it's positive, then it's going to be an exothermic reaction. So let's take a look at endothermic reactions. Same thing here. We have aluminum oxide being broken down into aluminum and oxygen. Decomposition reaction there. And if it's an endothermic reaction, again, that means heat is necessary to make the reaction happen. It's being absorbed. Then you're going to see a positive number here next to delta H. All right. And the other way you're going to see it is you're going to see that number written as one of the reactants. So on the left side of the arrow, which is showing that energy is going into the equation and is necessary for it to occur. Okay? So that's critical that you recognize, first of all, if a particular equation is endothermic or exothermic. Once we got that, we can move on to solving some actual problems here. So let's look at example 1 from your booklet. So first of all, is this an endothermic or exothermic reaction? And because the delta H is listed as negative, then we know that this is going to be an exothermic reaction because energy is being released. Okay? So part B, how much heat will be released when 1.48 grams of chlorine reacts with excess phosphorus? So just like we've been working on, we're going to map this out and we're going to circle the parts of the equation that we care about. And we're interested in chlorine. That's our given. And what we're trying to figure out is how much heat. So this is a little bit different. We're trying to figure out how much heat is released when that amount of chlorine reacts with excess phosphorus. So it might look like in the question that we care about phosphorus, but really what we're interested in here is chlorine and the amount of heat. And we're going to learn later on in the unit why why the word excess is used here. That will make more sense to you in about a week. So how do we solve this? In this particular case, we've been working left to right on the roadmap, but in this particular case, we're going to be starting on the right because we've been given a particular mass of chlorine. And before I do that, I should come up here and circle chlorine in the equation, and we also are going to need that amount of energy that is up there, okay? So we're going to start with a mass of chlorine right here, and then we're going to use the molar mass as a conversion factor, like we've done all year, to convert the grams of chlorine into moles of chlorine. And I should put a C here, because 2 there rather, because chlorine is one of these diatomic elements. And then lastly, we're going to use the delta H, which is also called the enthalpy, to convert from moles of chlorine into heat of chlorine. So I'm going to go ahead and write heat here again. That's a little bit redundant, but that's really what we're trying to convert to. All right. So that's our basic map we're going to use. And again, we're going to be working right to left in this particular case. So we're going to need to know the mass of just chlorine. We've got 2 of those. And when you add that up, you're going to get 70.9 grams per mole. So we're going to need that number. And then let's move down here. Our starting number and unit was 1.48 grams. And that's again of chlorine. And what we're trying to figure out is we're trying to figure out how much heat is released. So that is going to be our ending unit. And actually, the ending unit, heat is not the unit. The unit is going to be kilojoules, so we'll put that in there. Okay, our conversion factor. So when we go up to our map, our first conversion factor here is going to be the molar mass of chlorine. So that's going to enable us to convert from grams of chlorine to moles of chlorine. So for every 70.9 grams of chlorine, we have 1 mole. That is our first conversion factor, okay? Then, and we're only going to need 2 conversion factors here. This is simpler than what we've been working on recently. We're going to make this conversion from moles of chlorine into heat, and for that we're going to use the delta H here, the change in energy, and we get that from the question right here. So, and notice that chlorine, we have 5 moles of chlorine for every negative 886 kilojoules of energy that is released. So that's going to be our conversion factor. So for every 5 moles of chlorine, we get negative 886 kilojoules. So that's our basic map. So we're going to, as always, put our starting number and unit down here, 1.48 grams, and we're only working with chlorine.
Please come to the main office. David Schmoll, Jared Schneider, and Aiden Maima to the main office.
So I don't need to keep writing chlorine here since that's the only chemical that we are working with. So I'm going to put the molar mass of chlorine down here. And that's going to enable me to convert from grams to moles. And then I'm going to use my second conversion factor to convert from moles into kilojoules. And I arrange it like that so that I can cancel out moles, and that leaves me with an answer in kilojoules. And when I do my math there, I'm going to get negative 3.7 kilojoules. So the way we type that into the calculator is 1.48 times negative 886 divided by 70.9 divided by 5, and then we hit enter on the last step. So, and don't be intimidated by the negative number. All that means is that the energy was released. 3.7 kilojoules of energy was released in this chemical reaction. All right, so pause the video and give the U-try a try, and then come back and I'll show you the solution. Welcome back. Let's do the U-try together. Part A here says, is the reaction endothermic or exothermic? In this case, we have the energy on the reactant side, and it's positive, so that means it's going to be endothermic because it's showing that the energy is necessary to make this reaction occur. All right, so we use a positive number there. And then the question that we're trying to solve is how much heat, so again, that's what we're trying to figure out, will be absorbed when 13.7 grams of nitrogen, that's what we've been given, reacts with excess oxygen. So again, it might look like we're interested in oxygen here, but oxygen is not really a factor here in our solution. So we're going to start on the right side with grams of N2. We're going to use our molar mass to convert to moles of N2. And then finally, we're going to use our delta H here to convert to heat. All right, so that's our basic math. So we're going to need to know the mass of N2, which is 28.014. That's the mass of nitrogen times 2. And then we're going to plug everything in, just like we did on our first example. So our starting number in the unit was 13.7 grams. Our ending unit is going to be kilojoules, which again is our unit of heat. And my first conversion factor is going to be 28.014 grams of nitrogen is equal to 1 mole. And then my second conversion factor I get from the equation, and it's for every 1 mole of N2, I'm going to have 180 kilojoules of energy absorbed. And it's 1 mole in this case because there's no coefficient next to the N2, so that's the same as a 1, remember. All right, now we plug everything in, 13.7 grams of N2. We don't need to write N2 because this is all about nitrogen. And my mass of N2 per mole is 28.014 grams. And for every 1 mole of N2, I get 180 kilojoules absorbed. So then I times on top, 13.7 times 180. Then I divide down, so divided by 28.014, I hit enter, and I get 88 kilojoules of energy absorbed for every 13.7 grams of nitrogen. Okay, thank you for watching the video. Please reach out if you have any additional questions. Have a great day.